All right, recording's rolling. It is Wednesday, September 10th. We're on lesson 1-6, which is on page 53. This is transformations. So this is where you're going to take a parent function and you can stretch it vertically or horizontally. It's called dilations, or you can shift it vertically or horizontally. It's called translation. Right. So your guys' homework is on Alex. It should be labeled lesson 1-5A, 1-5, and 1-6. Okay, so we did 1-5A and 1-5 last couple of days. We're doing 1-6 today. This is, of course, due on Friday. I'll give you guys tomorrow, Thursday, to work on Alex in class, and I can walk around and troubleshoot any individual questions you guys have. And there's a quiz on Module 1 on Friday. You guys can, of course, all these videos are uploaded to Google Classroom. You can review anything that we've done for Module 1. Today, there's going to be reunification drill during period 6. Well, I've heard period 6 or period 7, so it's one or the other. So reunification drill coming up. So we're looking on, again, page 53. This is lesson 1-6, transformation of functions. So we're going to start, it says a family of graphs starts from some parent graph, right? So some basic graph you could do, right? And they give 4 examples down here. And then we're going to put this through some transformations to either dilate it horizontally or vertically, or to translate it. That's to say to shift it either horizontally or vertically, right? So you guys should know these very basic graphs. If you have f of x equals a constant, it's just a flat line. If you have like y equals mx plus b, yeah, some kind of line looks like this. Like y equals x would just be a 45-degree diagonal line. Now, yesterday, you guys saw this absolute value of x, just this classic V shape. Some of you guys knew that from previous years. Some of you guys saw it for the first time yesterday, but not everybody knows it. So f of x equals absolute value of x, just a very, very simple V. And then there's this parabola, which I think everybody knows. So f of x equals x squared is just a very simple parabola. So 0, 0 is a point that's down here at this vertex. You got 1, 1 is the point. You got 2, 4, because 2 squared is 4. 3 squared is 9, so 3, 9 can be a point right here. Okay, so get this parabola shape. Okay. So going in order to the book. First, it talks about translations, which is like shifting it. So they do horizontal translations. Actually, no, they start with vertical, which is actually, I think, a little bit easier to understand conceptually. So if you see the function and it says plus something after the function, that just means shift it up. If you see like minus something, you shift it down. Now, if you see the plus or minus tagged directly to the x, and that's like inside the function, that'd be a horizontal translation. So hold on to that. We'll come back to that again. Let's start with some vertical translations. Give you guys some examples. All right, so this is page 53. Right, so let's start with vertical translations. Okay. So what if I have a parent function, f of x? I'll just make it very simply x squared, which you guys know, of course, is just this parabola right here. So we're going to start that as the parent function. This is my, I'll list this as the parent function. Okay. Now I'll put this through some transformations, some translations in this case. So here, 2 different ink colors. Let's go pink, we'll do g of x. Okay. Let's make that f of x, and then we'll do like about plus 3. Right? Or you might see it this way. If this is f of x, wouldn't that just be plain x squared and then plus 3, like that? Okay. And then later on, I'll do an h of x, and I'll do that in blue ink. Ooh. What if you have the function, and then after the function, you do like minus 2? How about that? Okay. Or in this case, instead of x is x squared, it'd be x squared, and then minus 2. Okay. So let's graph all of these, and then what should the graphs look like according to these translation rules? So this would be, in this case here, it calls up 3, or this could be down 2. That's it. That's the rules. All right, so up 3 or down 2. There are different functions going on. All right, so let's go x-axis here. Let's go y-axis here. Go. All right. So my basic f of x is x squared. So that'd be the point 0 here. I should make a table just in case you don't know what this looks like. right? But I'm going to use this as my primary parent function example for the rest of today, right? So if I plug in 0 for x, 0 squared is 0. If I plug in, here, we go -1, -2, let's do 1 and 2, just to, right. So -1 squared is positive 1. -2 being squared is positive 4. 1 squared is 1, 2 squared is 4. Right. So I have some coordinates here. I have 0, 0, -1, 1, -2, 4. I have 2, 4. Oh, whoops, this is the one, 1, 1. Okay. If I throw in 3, 3 squared is 9. So 3, 9 is, I can fit that too. And then opposite side, -3, 9. Okay. So all these points exist on this parabola right here. A nice basic parabola that's -2, 4, so good idea. Okay. Okay. So I'll label that f of x. So in black ink is just my parent function, f of x. I'll use that throughout today. Okay, great. Parabola. Okay. Now, according to these translation rules, if you see the function and then +3 after the fact, you should be able to just take the whole thing and shift it up 3. So this point 0, 0 becomes 0, 3. The point 1, 1 becomes 1, 4. Right, so everything just shifts up by 3 units. Okay. It should look like this. And this, I'll label this g of x for pink. Okay. And then I'll switch over to blue ink to do h of x. So that should be the parent function just shifted down 2. So whole thing shifts down 2. This shifts down 2, down 2. This was the point 2, 4. If that shifts down 2, it brings it down about here. And same thing on the side. Okay. So it should look like this blue looking curve here that I'll label h of x. Okay. So that should be true, but is it? So let's set up some XY tables, and I'll stick to my colors. So let's do x and then g of x. I guess this would have been just plain f of x here, right? For that one. And then I'll switch over to blue ink. We'll do x, and then what is h of x, all in blue, right? If you were like totally lost in the woods and you had no idea what any of these curves look like, you could always do this. You could just make up some points. Make 2, make 1, 0, 1, 2, and see what happens. Make 2, 1, 0, 1, 2. Okay. And once you get enough coordinates on the board, then it'll naturally start to plot the graph itself. So let's make it. Okay, so let's see. If I take -2, plug it here. -2 squared is positive 4, plus 3 is 7. -1 squared is 1. +3 is 4. 0 squared is 0, +3 is 3. 1 squared is 1, +3 is 4. 2 squared is 4, +3 is 7. Okay. Does that work? Does that actually map to this pink curve? Let's see if it does. So back to up 7. Oh yeah, that's right on the curve, right there. -1, comma 4. Right there, always was. 0, 3. Right there, 1, 4. 2, 7. See, over 2, up 7. That's right there, actually, right there, point, point. All right, yeah. So all the points are lining up exactly where they're supposed to be. Everything's good. Okay. Okay. Now, what about h of x? Now, supposedly it should have been parent function x squared, just shift it down to, which I already drew. But let's see if I plug in the points, does that actually work? So -2 being squared is 4, -2 brings me down to 2. Okay. -1 squared is 1, -2 is -1. 0 squared -2 is -2. This finishes 1 squared. This 2 is -1. 2 squared is 4 minus 2 is 2. Okay. So -2, 2. So -2, comma 2. Yep, right on the curve. -1, -1, -1. So back 1, down 1. Right on the curve. 0, -2. Right here on the vertex. 1, -1. Right here. 2, 2. So over 2, up 2. Over 2, up 2. We're right there. Yep. Everything's aligned. It's exactly like the translations predicted it should have been. So these are vertical translations. You see the function, and then plus or minus something, you just shift it up or down a much. That's it. That's it. Okay. Now, let's go into the horizontal translations, which are listed on the same page. They're like right at the bottom here. Okay. Now, these are a little trickier to think about. Anything horizontal is usually opposite of your intuition. So we're still on page 53. Okay. But now we're switching over to horizontal translations. Okay. So I'm going to take my parent function. Here, let's spell it again. Parent function. I'll use f of x. All right, let's say it's x squared. Okay, sticking to that. Okay. Now, what if you have a g of x this time that's right, not, right, you have to remember for the vertical, I listed out the function and did plus 3 after the fact. Okay. Now, I'll do something that looks kind of similar, but it's actually a little different. What if it's f of, and then x plus 3 in parentheses? And how that would work out here is it'd be, in parentheses, I'd have x plus 3, and the whole thing would be squared. Right? And then we'll look at h of x. What happens when you um, take f of x and say, what if I do minus 2? So it could be like this, right? The x minus 2 collectively squared, like that. Right? Okay. Now, I'm telling you horizontal translation, so this has something to do with right or left, right? But it might be opposite of your intuition. Remember how for the vertical, plus was up and minus was down? Okay. Well, for horizontal, when you see plus, it actually means go to the left. So this indicate left 3. Right? Same thing here, left 3. And then if you see minus, that means go to the right. In this case, 2 units. So the right 2. Okay? All right, now I'm making that claim. Let's actually graph all 3 of these, and then I'll make XY tables, and we'll see does this actually measure up? Is it what I'm claiming it is? Okay? So we got x-axis, y-axis, go. Okay, let's do it. All right, so f of x equals x squared. Set up some tables. Let's do x and f of x table. I mean, I'll need this anyway later. Let's do x and g of x table for this peak. Right, and I'll come in with this blue. Let's do x and h of x for the blue. Right. See how this works. So if I pick -2, -1, 0, 1, 2. So very simply square it. That's what we did before. 4, 1, 0, 1, 4. I'm just square them all. Okay. We already did that before. Okay. Okay. We did that. We did that right here a few minutes ago. Okay. So 0, 0, -1, 1, 1, 1, -2, 4, 2, 4. Okay. So here's the parent function. Right. This is that very basic parabola f of x equals x squared. That's all. Right. So got that one. Right. That's the parent function. That's the parent function in black. Right. Now let's take that and okay, according to this translation rule, this plus 3 should mean go to the left 3. Now, I'll assume that's true, and I'll go back and test it later by plugging in some points. So if you take the whole thing and shift to the left 3, that'd be this vertex comes left 3, this point is -4, 1, this point is -3, 1, right there. And then, see, this point comes 1, 2, 3 over is like right here. Okay, so I think it's going to look like this, and then it goes way up. Right? It eventually does cross the y-axis, but way up here, right? And then for this blue, I said, so -2 means go to the right 2. Right? So take the parent function and shift it to the right 2. So 0.20 right here. Then this point to the right 2, this point to the right 2, this point to the right 2. Ooh, interesting. Lands on the y-axis. That looks like a vertical intercept, right? The y-axis intercept, vertical intercept. Right. So I think h of x is going to be that blue curve right there, and then g of x should be this pink curve, or at least I'm claiming that's true. Now let's actually put that to the test by making these xy tables, which again, you could have started with the xy tables. Again, if you were totally lost or if you wanted to discover this from scratch yourself. Okay. Now this pink curve, just looking on the graph, I see it's kind of back here centered around -3. So I'm going to pick, how about -4, -3, -2, -1. I'm interested to see what is the y-intercept, so I'll plug in 0. Okay? And this blue curve, this h of x, looks like it's centered around 2. X is 2. So I'll go about 0, 1, 2, 3. Okay. That should take care of it. Okay? All right, so see g of x. See if I plug -4 in here. -4 plus 3 is -1. Squared is +1. -3 plus 3, well, that zeroes out, so squared is still 0. -2 plus 3, that's 1. Squared is 1. -1 plus 3, that's 2. Squared is 4. And then if I plug in 0, I get 3 squared is 9. Okay. Does that work? See, -4 or 1. -4 and 1. That's that one right there. Oh, yeah. How about -3, 0? Right there. Oh, yeah. -2, 1. right there. Oh yeah. Negative 1, 4. Negative 1, 4. Oh yeah. 0, 9. Now that's kind of off my picture, but this problem would cross way up here. Like kept going, cross way up here. That would be 0, 9. All right, how about this blue curve, this h of x? So if I do 0 minus 2, that's negative 2 squared is 4. 1 minus 2 is negative 1 squared is positive 1. 2 minus 2 is 0 squared is 0. 3 minus 2 is 1 squared is 1. Okay, so 0, 4. Oh yeah, it's right here. Here's 0, 4. 1, 1. So 1, right there. Oh yeah. 2, 0. Oh yeah, vertex. 3, 1. Right there. Oh yeah. Of course, I could do like a million points. They would all land on each of those curves, whichever function comes. That's there. So that's the rule. Right? Okay, so again, this is pretty similar. So here's a recap so far. If you see the function and then like plus something after, it moves up, or minus something after, it moves down. Okay. But if you see the plus or minus tagged to the x itself, like it's inside the function, and then the function operates after the fact, okay? And that's a horizontal translation. And plus means to move to the left, and minus means to move to the right. And that's exactly what this shows. All right, so we're good so far. Good so far. All right, what's next here? Boom. All right, I've got dilations. So we're doing horizontal dilations and vertical dilations. I think vertical dilations are a little bit easier to digest. So I'm going to start with those and we'll branch out from there. So got page 55. Vertical dilation. Okay. So I'll start off with the parent function f of x. Let's just say it's x squared, just to stick what I've been doing. Let's have, what if g of x is like, um, let's have it as 2 times f of x, which in this case would work out as 2 times x squared. Right? And then, wait, what else do I want to do with this? Is that actually, that's kind of okay. I'll throw in another one just to show you guys something a little different. Let's do h of x. Let me make this negative. How about that? Let's do how about 1/2 of f of x, okay. Which in this case would be negative 1/2 of x squared. Okay. I wonder what that's going to look like. So this 2 right here means a vertical stretch by a factor of 2, so times 2. Right? And the 1/2 factor would be going to squash it like half the height. Right? So this 2 in front of the whole function, take a whole function times 2. It's going to stretch out the whole thing vertically. And this 1/2 is going to squash it vertically. So let's check this out. Now, you know your f of x is x squared because we just did a bunch of those. So excellent. So you know y equals x squared good. You got 0, 0, 1, 1, 2, 4. Right? We just did a bunch of these parabolas. Right? So you know that's your parent function right there. This is f of x equals x squared is that flat parabola, which you guys have seen several times already. Right? Now, what if you multiply each y coordinate by a factor of 2? Well, that would just double everything. So now 0, 0 is going to stay locked in place because 0 times 2 is still 0. But what's 1 doubled? Well, that's 2. Now, this is the point 2, 4. If I double that, that brings me all up to 8, which is kind of like up here. Right? So I think my g of x is going to look like this. And then other side, I'll do like the same thing. It'll come up like this. So this should be my g of x right here in peak, right, which is, of course, this function right there. And then what about the h of x? And my h of x, I said it was like half the size. But oh, one more detail. I see it's negative. Guess what the negative does? It flips it upside down. Okay. So if I flip the parabola upside down, it would look like a frown. And then also each y coordinate is going to be half of its original value. So here at 0, 1, well, upside down would be at 0, negative 1, but then half that value would be like half right here. Okay. Okay, 0, 0, flip upside down, half is still at 0, 0. Okay. Then what about the point 2, 4 right here? I should label that, make this really obvious. This right here is the point 2, comma 4. So if I flip that upside down, that's at 2, -4. But then half of that value should be 2, -2. Should be like the same thing on the opposite side because there's y-axis symmetry, there's vertical symmetry. Okay? And I think this parabola is going to look more flattened out. See how it's more flattened out? See my parent function looks like this. Okay? Times 2 makes it tall and skinny. And then a 1/2 value, negative, is upside down, but it's also kind of flat. It's kind of flat. If I just turned it upside down, they kind of dash this off. So this is, of course, my h of x. Right here is this blue. Right? I'm going to dash off and what if I just made it negative? To the parent function made negative. Get this point here, get this point here. So I'll just dash that, okay, just to show you. So this is sort of fourth function right here. Okay? So this is negative f of x that I dash in black ink. Right? Okay. And then half that break into the blue one. Right? Now, is that really true? Let's test it with some xy tables. So I'll do x and g of x. And then let's do x and h of x. Okay. All right, so now I do see everything's kind of centered around the y-axis, so I can go about -2, -1, 0, 1, 2. See what happens. And the same thing over here, -2, -1, 0, 1, 2. All right. All right, so g of x. Let's see, if I plug in -2 here and I square that, that would give me +4 times 2 is 8. If I plug in -1, square that, that's 1 times 2 is 2. 0 squared, that whole thing zeroes out. 1 squared is 1 times 2 is 2. And 2 squared is 4 times 2 is 8. Okay, so these points on that, -2, 8. -2, 8, that's right here. Oh yeah, oh yeah. -1, 2. -1, 2. Right there. Oh yeah. 0, 0. Around the origin. Oh yeah, vertex. 1, 2 over 1 of 2. Right there. And 2, comma 8 over 2 of 8. Oh yeah, right where I thought it was going to be. Okay. Right, how about h of x? Is this really the function? Does this really work? Let's see. So if I plug in -2 here, now -2 squared is +4. Half of that would be 2, and it's also negative. So it should be getting -2 overall. If I plug in -1, it's squared that as +1. Then half that, of course, is -half. If I plug in 0, the whole thing zeroes out. 1 squared is 1, -1/2. And then 2 squared is 4, -half of that brings me to -2. So these coordinates say -2, -2, -2, -2. Oh yeah. -1, -1/2. Oh yeah. 0, 0. Oh yeah. 1, 1/2, -1/2. Oh yeah. Over 2 down 2. 2 down 2. Right there. Oh yeah. Yeah, everything lined up exactly. Right. So these translations are working exactly as promised. Right, so I got one more dilation to show you guys. Right, and this was maybe the trickiest one to think about. It's this horizontal dilation here. Okay, so horizontal dilation. So still on page 55. Page 55, we're doing horizontal dilation. Okay. All right, so I'm just going to start with my parent function, f of x equals x squared. Okay. Now, how could I sort of like stretch or squeeze this horizontally? Okay. So we'll do g of x. I'm going to throw a factor of 2 onto x, but then I'll square the whole thing after the fact. Just remember, here, if I go back a couple slides to something else that says horizontal, this horizontal translation was if I tag like plus or something directly to the x, and then I push it through the function after the fact. That made it a horizontal type translation. Okay. Now over here, the fact that I tied the 2 directly to the x means it's going to be a dilation, but it's not vertical in the sense that I pulled it out. Right. Right, it's being pushed through the function after the fact. Right. So this means actually what this ends up being is a horizontal. Now this one's kind of counterintuitive. Anything horizontal is kind of counterintuitive. It sort of works opposite of the rules of vertical. So this is a horizontal squeeze, not a stretch, but a squeeze. So it's like being squeezed in by a factor of 2. Right. Or if you like, that's to say, half as wide as the parent function. Parent function. Right, half as wide. Okay. Uh, so in this case, this would look like, oh, whoops, I meant to do this the other way. I meant to say f of 2x, right? But you guys get the idea. It's the same thing, right? Same thing. Right? And then let's come up with an h of x. H of x. Right? What if I go the other way? What if I throw a 1/2 factor on here and I square that? And that's to say you take the parent function of like 1/2 x, right? This should actually, this right here means it's sort of like twice as wide as the parent function. So it like stretches it out. So whatever number is tagged onto the x, uh, take the reciprocal, and that's how you multiply it horizontally. Okay? So let's look at the graphical example here. So we got x, y. Let's go. I think that should handle everything we need right here. Okay. So y is x squared. Now you guys have seen that one a few times now. 0, 0. 1 squared is 1. 2 squared is 4. And then -1 squared is 1. -2 being squared is also 4. Okay. So there's your classic parent function, f of x equals x squared. Okay. So we got f of x equals x squared. All right. So we got that one on the board. Okay. Okay. Now, according to this translation, I'm saying if you tag a 2 to the x, okay, it should squeeze it by a factor of 2. So all these x coordinates, you can make half of their original value. Like, okay, so 0, half of 0 is still 0. But what's half of 1 would be a half. So right here. And same thing on the negative side, right here. What's half of 2 is only 1. Should be right here at 0.14. Ooh. And then over here, half of -2 is -1. It's right here. Okay. So I'm claiming that this is going to be like a really horizontally squeezed curve. Should be your g of x. See, it's like horizontally squeezed sort of by a factor of 2, right? Or 1/2 if you think in terms of reciprocals, right? Right. Now, interestingly, here's something else I want you guys to see. You could expand this out. Guys, is this the same thing as, um, well, here, I'll write it into space right here. Can I say this? Can I say g of x, which is 2x quantity squared? Is that the same thing as, can I square this? 4 times x squared? Right? And actually, if you interpret it that way, you guys do see this is the same thing. It might be easier to interpret because couldn't this be a vertical stretch of a factor of 4? It should be identical. A vertical stretch of factor of 4. Right? Is that really true? That means like this point, I'm going back to the parent curve, to this black parabola. I know one of the points was 1, 1 right here, 1 comma 1. What happens if I stretch that vertically by a factor of 4? Well, 1 times 4 is 2, 3, 4. Hey, what is that point right there? So 4 times x squared is the same thing as 2x quantity squared. So whether you interpret that as a horizontal squeeze by a factor of 2 or a vertical stretch by a factor of 4, either way, it's the same thing. Right? All right, let's try it for h of x. So now I'm claiming that here should be twice as wide. So whatever's tagged to the x, take the reciprocal. Right? 1/2 reciprocal is 2. Right? So it should be able to make this twice as wide. So 1, 1 was a point. So now 2, 1 should be a point. Right? And then on the parent curve, 2, 4 was a point. So twice as wide would bring you to 4, 4. So I think 4, 4 should be a point. Right? The point 2, comma 1 should be a point. Right? And this will sweep it. It's now I got a really wide looking parabola. That's my h of x right here. Really wide parabola. And same thing on the other side. Go back here. Okay, it's gonna kind of go up that way. All right, that's my h of x. So let's put this to the table test. Table test. All right, let's go x, and what is the resulting g of x? All right, and then we'll go what is x, and what is the resulting h of x? Right, so we'll try all these. All right, so now I do see this pink one's really skinny, so let's go about -1, 0. I'll throw a 1/2 in there. We'll see what happens, and I'll throw in 1. Okay. And then this blue one should be really wide, so maybe I'll go like -2, 0, 2, 4. Okay, just starting sort of what I'm predicting from the answer. These coordinates should work out to really nice numbers. Let's see if they do. So if I plug -1 into here, let's say -1 times 2 is -2, squared is 4. If I plug in 0, this whole thing zeroes out, square is still 0. If I plug in a half, well, 2 times a half is 1, squared is 1. And if I plug in 1 times 2 is 2, squared is 4. Okay, do these points really align? Let's see. Negative 1, 4. That's this point right here. Negative 1, 4. Oh, yeah. About 0, 0. Oh, yeah. Right here, vertex. 1 half, 1. So if I go over a half a unit and up 1. Oh, yeah, it does. It's right on the curve, right there. Then over 1 up 4. It's right there. Yeah, it works. It totally works. Yeah. All right, let's see. Does this blue curve h of x work? Let's see if it does. So negative 2, if I plug in negative 2 here, negative 2 times a half is negative 1, squared is positive 1. 0, well, squared is 0. Okay. 2, 1 half times 2 is 1, squared is 1. If I plug in 4, half of 4 is 2, squared is 4. Okay? See, so negative 2, 1, back 2, up 1. That's that point right there. Oh, yeah. 0, 0. Oh, yeah. Over 2, up 1. Oh, and I got it labeled. 2, comma 1. I was predicting that. And then the last one's 4, 4, over 4, up 4. Oh, and I got that one labeled also. Right there. Yeah. So everything's working. Yeah, so all these shift rules are working. Okay? They're all working. Now, your book goes on to say, what if there's like multiple transformations? Or they went with an absolute value for this parent function. Like, how could you like flip it upside down and shift it to the left and up a little bit? Right, you've got multiple transformations. So here, I'll make up my own example. Okay. So this is on it's sort of page 57 is where they talk about multiple transformations. Okay. So here, let's have my parent function. I'm going to stick to that parabola since I've been using that all along. So f of x equals x squared. Okay. And then for g of x, I'm going to do something really complicated. We'll just do f of x and g of x just for this one. Okay. So what if I come up with, I think what I want to do here, could do it. I want to do 1/4 of f of, let's do 2. I'll do x minus 3, and the whole thing, let's say minus 1. So that. Okay. Okay. And now I'm saying f of, no, that's really general. Now, since f of x is x squared, what that really is, g of x, in terms of this parent function, is I got 1/4. I got, okay, x squared. So this is 2 x minus 3, see, all being squared, and then minus 1 after the fact. So that's how this general function applies to this specific parent function. Okay. Okay. So according to what I've been telling you guys, this bit right here is 1/4 represents a vertical dilation. It's sort of like times 1/4, right? So this kind of makes it right, really flat, right? This 2 is a horizontal dilation. Remember, horizontal everything's sort of backwards from your intuition, so it doesn't make it twice as wide. It actually makes it like twice as skinny. Or I could say this. I could take the reciprocal. So I could do 1/2. So like reciprocal 1/2. That's what we did a few minutes ago. Okay. All right, this minus 3 tells you to move 3 to the right. And horizontal, everything's sort of backwards. So minus 3 really needs to the right. And then after the whole function, well, there's one more bit, which is this minus 1 tag on the end. That means 1 down, right, vertically. Okay, vertically, right? One detail I want you guys to notice is that notice I did sort of factor out this horizontal stretch factor of 2. So like if I didn't do that, these rules wouldn't work exactly right. Okay, so you do have to factor it out. Okay. Now there's a lot we're juggling here. So let's make these functions, see what this actually looks like, and then I'll put it to a table test. See, does this whole thing really work? 3 right, 1 down. X, Y. Okay, so my parent function, I'll just grab right here. X squared. So 0 squared is 0, negative 1 squared is 1, negative 2 squared is 4, 1 squared is 1, 2 squared is 4. Okay. Zzz, zzz. All right, so there's my parent function, f of x. Okay, just like it's been all along. Okay. Okay, now I'm claiming if these transformation rules are correct, if they work. Okay. I think I should just be able to follow these rules and everything's going to work out. Okay. So here, let's do the shifts first. Okay, 3 right, 1 down. I can start from this vertex. Go 3 right, 1 down. The new vertex should be right here at 3 comma -1. Should be the new vertex. Right. And I got some parabola works out from that. Okay. Um, I wonder if I should have made this negative just for fun. Well, okay, I forgot to do that, so we'll see what you guys know if it was negative, it would just flip upside down, but here, let's put there. It's positive, so it'll stay right side up. All right. Now, if I think about like just this parent function being shifted here, I'll sort of dash this off. So if I just shifted it, but I don't dilate it, I can go see over one up one, it's over one up one, looks like this. Okay. It kind of takes this shape. Okay. Now I need a horizontal dilation of like a half. So the bigger number this is, the more it gets squeezed vertically. So wouldn't that make it look like this? Okay, it comes in like twice as this one. Okay. Okay. But there's also a vertical dilation that's a quarter. Ooh, and the tinier fraction this is, it's going to smash it down. Okay. Now, if you think about it, here, step back and look at the big picture. This horizontal dilation of 2 ultimately ends up being squared. What's 2 squared? It's 4. Now, if you multiply that by this 1/4 vertical, like smash this way, the reason I chose these numbers is because they sort of end up canceling out for this particular example. Okay? So yes, you're going to squeeze it horizontally, but then we smash it down vertically, and it turns out to be like y exactly on the original parabola that got shifted over in the first place. Okay? So I think this should be the answer to g of x right here. That should be g of x. Okay? Now let's put it through a table test. Okay? What is x? What is g of x? Okay? So it looks like this is all sort of centered around 3. This is 3 right here, right? Okay. So maybe I'll go here. I'm curious to know what the y-intercept is, but let's go 2, 3, 4, 5. How about that? So if I plug in 0, 0 minus 3 is -3 times 2 is 6. Squared is 36. A quarter of 36 is 9. Minus 1 is 8. 8. So 0, 8. Okay, I can kind of imagine that. So if I got 4 here, if I went up to 8, yeah, this parabola could totally go up here about. That's right, right? So 2. 2 minus 3 is -1. Times 2 is -2. Squared is positive 4. A quarter of 4 is 1. Minus 1 is 0. Okay? 3. If I plug in 3, this whole thing zeroes out. And then subtract 1, you get minus 1. If I plug in 4, 4 minus 3 is 1. Times 2 is 2. Squared is 4. Over 4 is 1. Minus 1 is 0. And then 5. See, 5 minus 3 is 2. Times 2 is 4. 4 squared is 16. 16 over 4 is 4. Minus 1 is 3. So these 5 coordinates should plot exactly on this peak parabola. So okay, 0, 8, I said I could believe that. It looks about right. Okay. 2, 0 over 2, 0. Oh, yeah. Right here. X-intercept. 2, 0. 3, -1. Oh, that's the vertex I got labeled to start with. Yeah. Okay. 4, 0. Other x-intercept right there. 5, 3 over 5 up here. That looks about right. 5, 3. I think 5, 3 is right here. Should been about that right. That's the point. 5, comma 3. Yeah. Yeah. It totally worked. It totally worked. Okay. So that's multiple transformations. Now it's juggling a lot. All right. So good there. All right. Let's jump into some book puzzles here. Do a few of these with the guys. All right. How about all right. Do that. Great. Let's do number 10 and then number 12. Right. So number 10. Okay. They give you the parent function as the absolute value of x. And so f of x equals the absolute value of x. Okay. So how do you get g of x? Now, it looks like g of x is identical to f of x. It's just shifted to the right one and down 2. So how do you do? Here, I'll spell it out. I need right 1 and down 2. Right? Right 1, down 2. Right? So g of x is, okay, well, if I want to go to the right one, I need to, inside the absolute value bars, do x minus 1. Okay, wouldn't that be to the right one? That's it. Right there. Okay. And then close the absolute value bar. And then outside the absolute value, do -2. And that's it. Okay. So that is the answer right there. Okay. Okay. You plot that, that will exactly give you that absolute value curve. Okay. But here, I'll draw it out for you guys to prove that that's actually true. So x, y, make a little xy table over here. XY table. Okay. So let's go 0, 1, 2, 3. Okay. So if I plug in 0, this comes out to 1, minus 2 is negative 1. If I plug in 1, this is 0, minus 2 is negative 2. 2 minus 1 is 1, minus 2 is negative 1. If I plug in 3, 3 minus 1 is 2, minus 2 is 0. Okay? So if I plot this point 0 minus 1, right there, over 1 minus 2, 2, negative 1, 3, 0. Okay, now this is an absolute value. And you guys remember from yesterday, this should be like a classic V shape. Right here, I'll throw in one more. What if I put in negative 1? See what happens. Negative 1 minus 1 is negative 2. The absolute value of that is positive 2. Minus 2 brings you back to 0. Negative 1, 0. Right there. Right? So yeah, I definitely see this classic V shape emerging. Okay. So this should be g of x right here, that classic V, with the vertex at 1 comma negative 2. Is that exactly what the book showed? Oh yeah, that's exactly g of x right there. Okay. So number 12. So we're back to our classic parabola for our parent function. And it looks like this needs to go left 2 down 4. Ooh. So number 2, we got f of x, the parent function is just x squared. Okay. We need to go left 2 down 4. So I'll call it g of x. So see, left 2. Well, left 2 would be x plus 2, and that's all being squared. Down 4 is like minus 4 after the fact. Right? That should be exactly it. Same thing. I will graph that, see if that actually works. X, Y, x cube, x table. Okay. So let's go negative 3, negative 2, negative 1, 0. Okay. So if I plug in negative 3, this comes out to negative 1. Squared is 1, minus 4 is minus 3. Negative 2, this zeroes out. Minus 4 is negative 4. If I plug in negative 1, this is 1. Squared is 1. Minus 4 is negative 3. If I plug in 0, this is 2 squared is 4. Minus 4 is 0. Okay, let's plot those points. So negative 3, right here. Negative 2, negative 4, right here. Negative 1, negative 3. 0, 0. Okay. And I know this is the basic parabola. I could plot as many points as I want, but I know this is going to create a parabola shape. Okay, and I've got enough points where I know what shape it's going to look like. Okay, so this looks like a parabola with a vertex at negative 2 comma negative 4, and it happens to go right through the origin. Is that what they gave us on number 12? Let me see if it is. Number 12. Oh yeah, that's exactly g of x. It's right there. It's the same thing. All right, so we're doing good so far. Doing good. What else? Okay. I've got some transformations here. Let's do, how about we'll do 29 and we'll do 39. We'll do those last two. Right? So 29. Right. 29 on page 61, by the way. Right. So how do you go from f of x is the parent function. We're just back to playing x squared, and we've been using for most of the examples today. Okay. I need this to do looks like two things. I need to shift right 2. So right 2, and also make it upside down. Upside down. Those two transformations. So I'll call that g of x. Okay. I should switch in color. So I don't know if that helps or not. Maybe. Okay. G of x. Okay. Equals. Okay. So right 2. So I'm going to take the parent function x squared. Right 2. I need to do x minus 2, and that's all being squared now. Okay. And then to turn it upside down, I need to tag a negative onto the front of it. Okay. And that should get me that graph exactly. So let's graph this and make sure that it all checks out. X-axis, y-axis. Okay. So here, make a little table over here. Got x, g of x. Okay. So let's go 0, 1, 2, 3, 4. Okay. So if I plug in 0, get negative 2 squared is positive 4, and then negative brings you to negative 4. Okay. 1 minus 2 is negative 1 squared is 1, and then it's negative 2. Well, this whole thing zeroes out. 3 minus 2 is 1, squared is 1, and then it's negative. 4 minus 2 is 2, squared is 4, and then it's negative. Okay, so plot those 5 points. See if this actually works. 0, negative 4, 1, negative 1, 2, 0, 3, negative 1, 4, negative 4. Looks like upside down parabola with the vertex at 2 comma 0, and there's definitely a y-intercept here at 0, negative 4, right? Is that exactly the transformation we were trying to make? Make sure it is. It's, oh yeah, there it is right there. Yeah, that's exactly the same thing. Exactly the same thing. Yeah, GX. So we nailed it. Got it. Okay. I'll do one more example here because there's some pretty good word questions, and I highlighted number 39, which models a rocket that you launch. Right? So you got height as a function of distance. Okay. Now, if you throw something up in the air, height as a function of time is definitely parabolic. And if you throw it in the air at some angle, it does move across the field at a constant speed, which means that height as a function of distance would also be a parabola. So this is an upside down parabola, which means the parent function is y equals x squared, which is exactly the example I've been using for this whole lesson. Okay? So that's nice. So what does it want you to do here? Okay. It says what type of function does the graph show? So we're looking at parabola. Right? This is a parabola. So the parent function is y equals x squared. Which axis has the parent function been reflected? Ooh. Now, if you take a parabola and you flip it over the y-axis, the vertical axis, well, it just becomes itself. So that doesn't really do anything. But if you flip it over the x-axis, it turns upside down, which makes it look kind of like this. So it's been reflected over the x-axis. The parent function has been reflected over the x-axis. How's the graph further been translated? Well, I see where the vertex is at 2581, so it looks like to the right 25, up 81. This is in terms of meters. What equation is true for the graph shown? Right now, if you can know that it's basically a parabola, I definitely see the vertex because that's labeled, it's given, and I can get a pretty good estimate for maybe what one of the intercepts is. There's enough information lying around where we can put this together. Okay. So we got here. Okay. So this is number 39. We're going to draw their graph first, and we need to reconstruct their graph kind of from scratch. Okay. Okay. So I'll call the vertical axis h for height, and this would be in meters. I'll call the horizontal axis, well, how about x, also in meters. Okay. And a few points on here. So it goes up to 81 meters high, and that's at 25 meters across. So we're right here. I'm just copying it straight out of the text. This is the point 25 across, 81 up. Those are both meters. Okay? Now, where it's at ground level, I'm going to take my best guess. Maybe, maybe about 15 meters, or it's about 15 meters across. If it's, notice that I'm just kind of estimating. That's probably pretty close though. Okay? If it's 10 meters before the peak horizontally, then guess what? It's going to hit the ground. I mean, doesn't a parabola have vertical axis symmetry? So it should be 10 meters after, which should be at the point 35 right here. Okay? So I think we've got a parabola upside down that basically looks like this. Okay? Looks like that. Okay? Okay, so the parent function could be, I'll call it f of x, is just x squared, because it's some version of a parabola. Right? We got to do a few things with this. We got to make this right 25. We got to move this up 81. We got to move this upside down. And also, I'll just say vertical stretch. We need an exact equation so that it goes through exactly these three labeled points. Like this is the point like 35 comma 0, and this is point 15 comma 0. Right, okay. You guys get the idea, right? Okay. Right. So how can I do that? Okay. So I'll say h of x equals. Okay. Now, so I know x squared is the parent function. So I can take x, let's see, right 25. Wouldn't that be minus 25 right here? Okay. And then squared. So that effectively moves it to right 25. Up 81 would be like plus 81 at the end after everything's done. Okay. But there's still one more factor. I'm going to throw some stretch factor A in front of the whole thing. Okay. Now, I don't know what A is, but we can solve for it because we know when it's at ground level, or we have a pretty good estimate. And that's both of these points here. So I think at the point 15, 0, this should be, I'm going to switch it color, make it stand out a little better. This right here is the point 15, comma 0, right? Right, maybe relative to like a tree or something. Maybe it's 15 feet, or sorry, 15 meters in front of a tree, and he launches the rocket there, and then it goes keeps on. Okay. So when this h of x is 0, that's like a y value, then that corresponds to this x being 15 meters away. Or I could put 35, and I should still get the exact same correct answer. Right? 25 is getting squared plus 81. Right? So this is when I plugged in this coordinate right here. I just plugged in 15, 0. So 15, 0. That's that right there. X, Y. Right? Right? In fact, if I did plug in 35, 0, you guys see the difference between 35 and 25 is 10. The difference between 15 and 25 is negative 10, but it's being squared. So yeah, it would definitely give me the same thing either way. So let's finish solving this up. So 0 equals a times, right? This would be, well, effectively negative 10 squared, which is 100, and then plus 81. Okay, finish this out here. So if I subtract the 81 over, that's negative 81 equals a times 100, and then divide both sides by 100. So a ends up being negative 81 over 100, or if you like, negative 0.81. Okay. Now that I have that, I can properly piece the whole equation together. So let's do that. So we'll piece the whole equation together, then we'll test some points and see if it looks like it's actually working. So h of x in general is, right, so it is this, except now I know what a is. We just got it. It's negative 81 over 100, and then times, and then here I have the negative, by the way, makes it upside down parabola, which it should have always been negative, and it is, so that's nice. We got x minus 25 collectively being squared, and I got a plus 81. I mean, right. So that should be the answer to number 39. That should be the answer. Okay. Now I do want to test that. So I'm going to come up with a table of values. Okay. We're going to push it through and see what happens. So I got x and I got h of x. Okay. We'll push it through the function and see if does it match the original graph straight from the book, which I basically have copied right here. Right, so I know there's something special going on at the x value of 15 meters, say, relative to the street, so I'll put 15. I know that at 25 meters, it should be reaching the peak, so it should go all the way up to 81. I know at 35 meters, it should be crashing back into the ground. And maybe just for fun, I'll pick a point kind of in the middle. How about, I wonder what's going on at about 20 meters or so. Let's see. Okay. Now, this little fancy ones here. So here's what I do. I'll do a calculator trick. Watch this. Negative 81 on 100 times, and then in parentheses, I'm going to do this. I'm going to do second answer. I'll treat this as an x. Minus 25 collectively squared, and then after the fact, plus 81. Okay. I'm going to put this out. Anyway, if I do 15, so my first x value is 15. Okay. So if I scroll up, where the answer is right here, it automatically plugs in 18. Oh, it gives me exactly 0. Oh, yeah. That is that point right there at 15, comma 0. Oh, yeah. Always there. What if I plug in 25? So 25, right, scroll up. Now, where the answer is, it puts 25, right? But you know what the answer should be, right? It's at 25, it's got to be 81 meters up. My calculator better say 81. If it doesn't, then I just ruined this whole video. Let's see. Oh, yeah, math wins again, 81. And at 35, if I plug in 35, enter, then scroll up, plug in 35 right here, it should bring me back to ground level. Oh yeah, it did. Right. And then just for funsies, if I plug in something, just some middle by, let's say 20. Now 20 seconds is right here, which looks like most of the way to the top. Like it's more than halfway to the top. So I don't know exactly what I'm going to get, but it's going to be between 40 and 80, right? More than 40, less than 80. It's got to be, right? Okay. Let's see. So I'm taking 20, I'm plugging it in. Let's see what happens. Oh yeah, sure is. 68.75. That is exactly right in line with what I was predicting. All right, so there you go. There. So there's transformations. So here's a recap of what we did. Right. Horizontal translation. Right. If you type the plus or minus something directly to the x and then push it through the function after, plus moves it to the left and minus moves it to the right. A vertical translation, you have the whole function, and after the fact, you do plus or minus, and that very simply plus moves up and minus moves down. You have that. Uh, the vertical dilation is if you have the whole function, and then after the fact, you multiply by some factor, it'll vertically stretch it. And if you have a negative value, it'll flip it upside down. Right? Now, probably the trickiest of all these dilations is the horizontal dilation. So this is if you tag some factor to the x, then it will uh, again, sort of counterintuitively do the opposite of what you want. So the bigger this number is tagged to the x, the more it squeezes it horizontally. And if it's a fraction, it'll actually stretch it. Okay? And then you could possibly sometimes actually factor that out and interpret it as a vertical stretch, and that might be more intuitive that way too. Okay. All right, and then here's all of it together. Need to go find this and dig this up. Okay. What if you wanted one with all the translations? So this is one where I did all these. So I got to the right 3, I got down 1, I got a factor 2 here, squeezes it by a factor 2, or you could say makes it half as wide, and then a factor 1/4 in front makes the whole thing squash vertically by 1/4. So there's all your transformations.